Yeah, like I was telling earlier, this series for pi was originally used for calculating, but extremely slow convergence. Like I said, you have to add some 5 billion terms to converge. Now, obviously, people have tried to find out faster converging series for valuation of pi and so on. I'll just quote one example name in that. One of the probably the fastest converging algorithm for pi was given by Srinivasan Ramanujan. Srinivasan Ramanujan is an Indian mathematician. Unfortunately, because of ill health, he died at the age of 32 or 33. But at such young age, he produced so many very interesting results. His interest was primarily in theory of numbers. He is reputed to have produced in his notebooks, like I think mentioned earlier, he used to do all his calculations on a slate with a piece of chalk and rub it out and write the final answer in a sheet of paper because paper was expensive, that is the time that he lived. He is supposedly to have produced something like 3,900 results. What is the result? Is some kind of a theorem or some result. Like for example, there is a series for pi. I won't even reproduce it here. You can always refer to Wikipedia to get that actual series, which converges so fast. Just the first term itself is accurate to some 10 decimal places. First two terms will give you accuracy up to 16 decimal places and so on. Some crazy speed of convergence. And out of these 3,900 results, after his death, there was a final last notebook that he had written at home. His wife has kept it and given it, and people have analyzed that also. And they have found, except for some 20, 30 of these announcements that he has made, rest of it is all perfect and correct. Okay, so accuracy is, what he has given is 99.99% correct. And most of the results are with the theory of numbers. And one of the results was actually recently used to prove Fermat's last theorem. See, there is a Fermat gave this theorem about I think 200-300 years ago, and is known as the Fermat's last theorem. He has given a lot of theorems, and one theorem for which he did not give proof. It is more like a postulate. Last postulate, which simply says, if you have an equation like a power n plus b power n is equal to c power n. A, B, C are integers. One familiar thing is a square plus b square equals c square. We know Pythagoras theorem. And we are looking at integral solutions only. That means ABC must be integers. For example, for n equal to 2, 3, 4, 5 is one result. 3 square plus 4 square is 5 square, or I think 5 square plus 12 square is 13 square, and so on. There are an infinite number of solutions when n equal to 2. But if n is greater than 2, like sum of 2 cubes is another cube. So Fermat said there is no integral solution. For any value greater than 2, there is no answer for this. That is his last theorem. One way of proving, or rather disproving it, is to give one example, saying, I'll give you ABC integers where a power 10 plus b power 10 is equal to c power 10. That immediately disproves Fermat's last theorem. That also people have not been able to give for 200 years or maybe more, 300 years. Nobody is able to prove it or disprove it, either way, right? Recently, and they had announced a prize also, some million something, whatever amount, I don't even recall the amount that they had announced. Millions of mathematicians have worked on this Fermat's last theorem, and it's not been possible for them to either prove it or disprove it, both ways, right? Now, Ramanujan actually didn't prove it, but he proved some results out of these, what I have listed. one of the results was used by somebody else to actually prove Fermat's last theorem. Now currently it is proved. It has been proved, and that gentleman also got a prize just about 2 years back or 1 year back or something. It's a very recent event which has happened. I'm saying that is the standard of Ramanujan's mathematical genius. He was a poor Indian. His only interest was in theory of numbers, not even mathematics. He was not interested in mathematics. Only numbers, 1, 2, 3, the theory of numbers. Therefore, every college or school he attended, he failed, obviously. So he didn't pass any of the exams, right? But then, that's the kind of genius he was. So, anyway, that is besides the point. Now, I'll not even bother giving you the series for pi. One of the series, he has given several converging series for valuation of pi. Now, today, some of the computer algorithms, fastest computers they use to evaluate pi to million decimal places and billion decimal places and so on, they have evaluated. And many of them use the series which Ramanujan has given. So, that is his level of influence in mathematics. In fact, based on his results, many new branches of number theory have been started and continued by others. Let me not, you can read about history if you are interested. All that information is available. That is fine. Now what I want to do is go to the next phase of our discussion. We saw Taylor series. There is actually something called Taylor's theorem also, which says that obviously if you want to evaluate a function, we can't add infinite number of terms. No way we can, no computer also can add. We are going to add some n number of terms which will be approximate value only. Now how far approximate it is and what is the error involved. So there is a Taylor's theorem which discusses that. I thought I would discuss that, but then I think it's beyond the scope of our discussion here. So let me not bother about that. So there is something beyond Taylor series also, as you understand, which you may be looking at in future. That is fine. Next, what I want to take up is this rigor of mathematics. No? In fact, most of this is a subject which is beyond the topic of our discussion here. How was this rigor is introduced? Because most of the proofs were intuitive, they felt, and we want a very, very rigorous proof of every statement that you make. Or if you can't make it, at least state that as an axiom, so that it is taken as granted. So rigor in mathematics is the question. Now, how do you achieve that? And one of the reasons why they did that also is a question that I would like to answer. For doing that, what we'll do is we'll take up one important assumption that we made, that is the intuition, intuitive parts that people have believed. Actually, there are two parallels to it. One is the Greek geometry itself is, if you look at the geometry, where we have a line segment which got infinite number of points, all we need to do is mark one of those points as 0, so that we get all the values to the right of that 0, we treat them as positive. Values that we get left of 0, we treat as negative. And every unique point here represents a real number. This is one way of specifying the set of real numbers is to use the Greek geometry, Euclidean geometry, and say real number line, every point on the line is a real number. Very simple. And an equivalent way is our Indian style, decimal positional number system. This was worked out in the first few centuries of Christian era, that is about 2000 years, 1800, 1900 years ago, by Indian mathematicians. And this position number system, it doesn't say how many decimals that you can have. We simply say an infinite number of decimals represents a real number. Both are equivalent actually. If you look at this number line, I have 1, 2, 3 and so on. Any point you take, we can always reach that by subdividing the two neighboring points into 10 pieces and selecting two more points, subdividing again by 10, subdividing again by 10. We keep doing that. We get the additional digits and we are saying infinite number of decimals is actually a valid real number. So both are equivalent actually. Both are equivalent definitions. If you use these two equivalent definitions of real numbers, obviously every other algebraic theorem that we have, or even every calculus theorem that we want to prove, can be proved. No questions on that. Now people were thinking that these two are an actually overkill of specifying real numbers. See, their problem was how to define real number without making this assumption, if we can define it. One of the main authors of that school is George, without the E, Cantor. With his set theory. Set theory, the entire theory was proposed to circumvent, basically to circumvent using one of these two as axioms in mathematics. We don't want to use these axioms. I want to specify my real numbers without these axioms. That's what they wanted to do. So how do you do that? So that means we have to take the properties of real numbers, list the properties. We'll have to make some assumptions, of course, but we specify them as axioms. So we specify a set of axioms which this set of numbers, is no more a number line or no more decimal digits, it's just a set of numbers. They satisfy these properties, then we say they are real. So what are those axioms? Now these axioms themselves are given in three different groups. So there is an axiom group A, then there is an axioms group B, then the axiom group C. And the set of entities, I won't even call them numbers, which satisfy all of these three axiom groups is a real number. Okay, that is the approach. That means we have to minimize the assumptions. Rest of it we prove also. We want to use the minimum number of axioms and any other property of real if we want, we have to prove using these axioms as given absolute truths. So we get a minimal set, So that is just like Euclid's elements specified those five, I listed the 5 axioms of geometry as given, and once those 5 are given, the rest of the geometry theorems, we should be able to prove it with rigor, without making any further assumptions. That's the basic general idea of rigor in mathematics is this, actually speaking. Now there are 2-3 things which happen to it. Why this has been done? One, of course, we want rigor. Everybody wants a rigor, so that's a universal understanding that we want the rigor. One reason, of course. Now, the second reason is, remember, all this whole development of science and mathematics in particular, actually they started, the developments, evolution started in Babylon and Babylonians and Indians and Iraqis and so on, that region. And later on only it shifted, the development or evolution shifted to Europe, and most of the other developments beyond that point have taken place in Europe. There is no questions on that. Now the Europeans, they want to cut off. It is something like, I'll give a simple analogical example of saying that if you look at a chimpanzee, ape, chimpanzee or orangutan, they look very similar to human beings. You see, they are very, in terms of even their behavior. Of course, they have a tail, I think, but anyway, we also have a vestige of a tail, I think, if you look carefully. But we have evolved beyond apes. But then humans, as a human psychology, as per Darwinian theory, every species has evolved from other species, right? So, species evolution, which has taken place, right? Now, as humans, we don't want to admit to a monkey or an ape, which is there right now in a zoo, saying, I got evolved from you, no? So, I don't want to do that, no? So, how do we solve this problem? Very simple. So, we got our Homo sapiens. We are the Homo sapiens, right? Sapiens. Of course, before we became Homo sapiens, we were something else, no? One other species I'll write, we were Homo erectus. Homo erectus is Homo which walks straight, no? Erect. We became erect, no? Unlike monkeys, they walk on all the four. They walk on 4 feet. We walk on 2 feet, no? So we become erect. So that is the Homo erectus, right? Now, ape is not a Homo erectus, no? So I don't want apes. I just write apes, chimpanzees, orangutans and all related species. I don't want to be saying I got evolved from apes. No, I don't want to do this. So what is the solution? Is we go backwards in time and say there was an earlier animal, some animal. It's not there now, it doesn't exist, okay? So we'll call it a proto-animal. Some animal proto, which had some distinguishing properties that evolved over a period of time to apes as one direction of evolution, and it evolved in the direction of Homo erectus and Homo sapiens in the end. So that means we are not directly related to apes. We didn't evolve from apes. They are our cousins, maybe something like that. So we would like to say that. So we don't want a direct dependence on apes. Same here. What I'm saying is European scientists don't want to say, how's your science today? No, we got evolved from Greek geometry or Indian. No, they don't want to say that. You understand? So they want a different approach. So we go backwards now. So that means we have to go back from this number line or the decimals which have a property of real numbers. We go back, redefine real number as something which doesn't probably contain all of these, and from there we derive. And so now we got our real numbers. And all our science is based, mathematics and science is based on that real. That is set theory. One possible explanation. Now the one more, third explanation for the same thing what they have done is, of course, this whole business has kept thousands of mathematicians busy and happy for the whole life doing research into saying in the set theory, you proved that theorem, then I will prove it now. There are so many research papers. Every year they keep producing research papers and people are making a living out of it. Finally, what have they done? Nothing. I mean, it was already there. What was already there? They are reinventing the wheel, no, basically. Basically, they are reinventing wheels. But then it keeps so many people busy and happy. I am sure today a lot of Indian mathematicians in research are doing the same thing. No? They are reinventing wheels. The same number theory and same real representation. I don't want to say anything against those people because they might be doing just for their living, of course, right? Or maybe there is some real fantastic idea, brilliant thinking. There is no question on it. This whole business is brilliant thinking. At least we have to give respect. I would like to give a tribute for the thinking, whether it's actually needed or not. See, mathematics is one subject where people engage themselves in, like number theory of Ramanujan, for example, engage themselves in, or Fermat's last theorem, who is bothered whether a power n plus b power n is c power n plus 1 or a c power n, no. I mean, nothing, it doesn't have anything to do with life, right? So it doesn't affect anybody in this life, on this earth. But then they spent their lifetime on it, on such issues. Mathematics is one subject where people spend time on something, doesn't look like it is useful, But you never know. You never know. At some point of time in future, maybe this becomes useful, right? Possible. That is another. Fourth reason, doesn't matter. Let us get back to our axioms that they defined. And those sets, that is, set of elements or items or set of whatever you want to call them, objects which satisfy the axioms A only, are what are called fields. So these are field axioms. Now what is a field? Field basically is a set of elements which satisfy some properties. Now the set of elements, as an example, I will assume whatever elements are right, like ABC or XYZ, they are belonging to that particular set. Let's just assume that. I don't want to specifically say this belongs to this belongs. I mean, we are not talking about anything else. In any case, so what is the first property of that? Of the axioms A is they are commutative. Obviously, a field has to be specified with the two operators. In arithmetic and algebra, we have four operators. So we have add, subtract, multiply, and divide. Now, I don't want to use all the four. So I want to minimize that. So we specify only two of them. So what are the operators? One is called the additive operator. I read that as plus. Actually, they call it additive operator. Something called additive. It's not our plus. Just plus, just a plus. And multiplicative. We don't specify division, we don't specify subtraction here. So that will become part of the rules. So first part is what is known as commutative. Commutative means A plus B is same as B plus A. Same as A star B is same as B star A. Commutative. So add this way or add that way, result is the same. First. Next, two is associative. These operators are associative. That means you can associate with either the left or the right. So which means I can write A plus of B plus C. I can add B and C. Now B is associated with C now. We do one addition and the result we add to A, right? Will be the same as A plus B plus C. Same thing for multiplication also. A star B star C, same as A star B star C. Same, no difference, okay. Then 3 is star is distributive over plus. So I'll just call it distributive. That means A star of B plus C. So the star gets distributed over the plus. Will be the same as A star B plus A star C. In fact, these are all our basic arithmetic rules. What they have written in field is set of arithmetic rules. Then 4 is there exist two unique numbers or two unique elements in the field. One is called the additive identity. We got two operators. For addition, there is one identity. For multiplication, there is one more identity. We write them as 0 and 1, of course. Additive identity, we write it as 0. Multiplicative identity, we write that as 1. So, which means 4 is existence of these identities. Additive and multiplicative. Five is a property of these identities is, I'll just write the property. A plus 0 is same as A. If we add additive identity, anything is the same, right? Similarly, B multiplied by 1 is same as B. Or A star 1 is A. Now, using these axioms, now they can define a new operator called divide or minus and so on. That can be worked out. So that's okay. Those are theorems, no? They are not axioms. So this set gives you what are called axioms A, Next comes ordering. Ordering comes under next set of axioms, set B. Basically, we order the field. When do you say I got a field which is ordered? We need a new operator. We need a relational operator. Actually, in arithmetic, we use 3 or 6 relational operators. Here we need just a single one, but we can derive the others using those. Let us say that operator is less than or equal to. Not less than. We define what is known as a less than or equal to. What is the meaning of that? It must have these following properties. Again, a set of properties. First property is it is reflexive. Reflexive is on self. That means A is less than or equal to A. Obvious, you understand? See, many of these are obvious statements as far as we are concerned, but they are defining as a set of axioms, and using only these, you should be able to prove rest of the algebra and arithmetic, basically. That is the challenge, I would say. That is the challenge of these discussions. Reflexive. Second one is they are anti-symmetric. Sorry, this relational operator is anti-symmetric. That means I got two elements, call them A and B. So I got A less than or equal to B is one relation, is already true, is correct. And we write as a like this. This is known as and. And we write like this, vertical less than or whatever you want to call it. And B is less than or equal to A. Both are true. If A is less than or equal to B and B is less than or equal to A, what does it imply? A equal to B. This is known as the anti-symmetric role of that. Now 3 is it is transitive. That means if A is less than or equal to B and B is less than or equal to C, which implies, this will definitely imply this equal to greater than, when I write this is known as implies in English. No? This is a short form we write. Implies A is less than or equal to C. It's transitive. No? This is the same here. If one point is the right of another point, which is to the right of a third point, first point must be right of the third point. These are all very obvious from the Greek geometry case, right? There is no questions on it. Transitive, that is the next property of that. Then we have one more, which is the totality. Totality means when you have two elements A and B, suppose I have got two elements, A must be less than or equal to B. This must be true. You are saying this is not true, or B must be less than or equal to A. One of them must be true, or both can be true. Of course, both can be true, like in the reflexive property. But at least one of them must be true. So when you write it like this is known as the R. This is the N, no? And R. So now you can see, if you read any modern algebra text, research paper, you're likely to find statements like these with these symbols. So I thought I will add those symbols also as part of our discussion. Okay? So now we'll come to the last part, axiom C, which is a bit tricky. That is where the whole discussion actually starts. There is one last, one last property of the axioms B which I did not mention, property number 5. That is this less than, this operator is retained across. It is a bit difficult to, we use that in inequalities across plus and star. And the behavior is slightly different because of negative numbers. You have to be very careful there. That means if A is less than or equal to B, let us assume, will definitely imply, I got a number C, one more number, A plus C will be definitely less than or equal to B plus C. This is it. In the case of multiplication, you have to be careful, because if that is a negative number, then the order will change. No? So you have to. So I should say A less than or equal to B and C is greater than 0. Then only it implies A multiplied by C is less than or equal to B, B multiplied by C. It's okay. We know this in arithmetic. When we have an inequality, we do this balancing, no? Mukabala, balancing. We add, subtract, multiply, divide, take inverse of, all that we do. There you have to be very careful that that inequality actually doesn't get reversed. So that is retained. That means the behavior of the relational operator over these operators, so additive and multiplicative. So now we go to the axioms C. Right? We need, this was actually sufficient for quite a few hundred years in mathematics, this much of axioms, but because the rational numbers satisfy this. Rational number set satisfies all of these. But the problem is rational numbers is they have holes. No? So we have the irrational numbers between rational numbers. No? So we have to fill in the hole. No? So how do we fill in the hole? Is the axioms C. Not axioms, axiom C. There is only one axiom here, which is actually called the completeness. We have to complete the set of numbers. Otherwise, we have a problem. Because reals satisfy these A and B, rational numbers also satisfy these. Right? So what is the difference between real and rational? Is a question of completeness. Now, how are reals complete and rationals not complete? Is the question, right? And what is that axiom? Only one axiom, right? Yeah, but the problem is what is that axiom? Again, different people have given different axioms for this completeness. Each of them is equivalent. You can use whatever axioms that you want. One of the axiom, any one of them. So it is not, see, these properties are 1 and 2 and 3 and 4 and 5. Here 1 and 2 and 3 and 4 and 5 all. Here it will be 1 R, 2 R, 3 R, you understand. And what is the first axiom for completeness is real line, Greek. And you can fall back on our own standard and saying every point on a line represents a real number. We'll complete the completeness. Everything is complete now. No gaps in reals because there is no gap in the line. Or we have a second one also, right? Or Indian, infinite decimal digits, infinite number of decimal digits. This also fills in all the gaps. Remember, when you say infinite number, need not be infinite. You say 0.40000. You don't have to write those. You don't have to actually write all those infinite decimal digits. But in the case of irrational numbers, you will have to write. I mean, they are there. Like square root 2 or pi actually has got infinite number of decimal digits. 1 over 3 or 1 over 7, for example, has got repeated set of infinite number of repeated blocks in terms of infinite number. It has got actually infinite number of decimal digits, but they repeat, blockwise they keep repeating. So you can show one repeat, like I'll give a simple example. 1 over 7 if you take is 0.14287 and again 1/4. These 6 digits keep repeating. So sometimes people write, they don't want to write again. They'll write a bar across this. That means that block is repeated infinite number of times. So it's 1 by 7. That's also fine. That is also real. I mean, these two already exist. Now, instead of these two, can I have something which is weaker? No? These are very strong axioms. No? See, they are looking for a weaker axiom so that you can prove the rest of this axiom using that weaker axiom. See, we want to give a minimal definition for reals. This is a big definition, huge definition for real. No? Maybe it's not really required. I'd like to give a weaker definition for reals so that the rest of the real completeness has to be the same. That question, square root 2 must be a real number. There is no question. Pi must be a real number. No question. But then I don't want to fill in square root 2 and pi by a huge axiom, which is assuming too much. I want to assume as little as possible as the axiom and then do that. What is that? That is the set. First among those is actually called least. You see, many of these actually sound so obvious, intuitively so correct that you refuse to believe that this is actually an axiom. Is known as a least upper bound property. In fact, this will distinguish between reals and rational numbers. Rational numbers won't have any of these axioms. It won't be true for rationals. But for reals, all of them will be true. That is the true test of that. Okay. Now, least upper bound property. What is the least upper bound property? Is if you have a set of elements and they have a bound. Bound means I can have upper bound, lower bound. So I am talking about upper bound here. Supposing I got a set of these numbers or whatever elements and they have an upper bound, we are saying they will have a least upper bound in the set. That is all we are saying. Very simple. Looks very straightforward. Yeah, but then rational numbers don't have this. I can have a set of rational numbers. Upper bound is there, but least upper bound is not there because that is a real number. No? Least upper bound usually will be a real number in the rational set, which doesn't exist. This is one property which completes real system. Then one more very obvious statement we make is known as the extreme value theorem. I mean, they call it a theorem, but this will be a theorem if you assume any of the other axioms. You can prove this theorem, of course. Then it becomes a theorem. Remember, all these axioms, you can treat them either as theorems or axioms. And one of the axioms will be an axiom. Rest of the axioms will become theorems. So that's why this is known as extreme value theorem. What is the extreme value theorem? It says that if I have got a function f which is continuous over a closed interval, let's say a comma b, then it has at least one, implies f has at least, this is a minimum, one set of extreme values. I am calling them extreme values. I could have called them maximum values and minimum value. I suppose maximum value is one extreme value, minimum value is one extreme value. That's the general thing. I am using a specific term called extreme values, not maximum is the overall maximum. No? So maximum is a global maximum. Extreme value could be a local maximum. No? That is, if you look at a function f. So let me just draw the graph for that. I got the x-axis here. I will draw the function f. I got the 2 points A and B, over which the function is continuous. See, the main requirement here is continuous. Continuity must be there. That means the successive values of f as x goes in its delta steps. If you take on x, f should take epsilon steps and reach wherever it has to go. Remember that. So that continuity is a must. So in this, I can have something like this. That means I got a maximum value. So this is the is like a global maximum, or I'll show you, I can draw several graphs here actually. Maybe I can rub this part, axioms A, and show you a few diagrams just to get you an idea of what I'm talking about. What is this extreme value theorem? What are these extreme values, right? Now, I'll just write the plot of f, yeah. Just visualize this x-axis A and B somewhere below. Just visualize that. One is, I got a straight line here, parallel to x-axis. Is there an extreme value there? Is there a minimum value? Everything is minimum, everything is maximum. Everything is extreme actually there. Correct? Complete extreme. No questions on it. Or I can have something like this, straight line, inclined line. Obviously, there is a minimum value and a maximum value within the interval. No? Fine. Next, third is minimum value is here. Maximum value is not this. It is actually higher than FB. This is FA, FB. I got a maximum there. It's a global maximum, right? Or now you see I got a global maximum here, but then there is one more maximum type of fellow, no? So is known as a local maximum. No? This is known as a local. In fact, even the global maximum is also a local. Locally also is a maximum. Globally also is a maximum. This is a locally a maximum. And what are those called? They are actually called, there are two names there for maximum and minimum extreme values. They are called extremum, supremum. They are called extremums. Extrema. Extreme values are called extrema. There are two extrema, local extrema. One is called a supremum, higher. Other one is infimum. Infima. Infimum is a minimum. Local minimum is called infimum. Local maximum is called supremum. This is actually called a supremum. This is called infimum. Local minimum is infimum, supremum. So now extreme value theorem simply says, because the function is continuous, when you go from one point to another point, we must have at least one supremum and at least one infimum. Now you try drawing these Euclidean geometry graphs of f, which are continuous, of course, you will find that is true, correct now? You understand? So extreme value theorem takes care of these gaps in the rational number system. Is one more axiom, extreme value theorem. Very nice. Then we come to the fifth axiom, which is also equivalent. Intermediate value theorem. I have talked of this as part of our analogies, earlier sessions, saying MLA Shastri is here right now in front of you. After 10 minutes, if you see MLA Shastri is outside that, in the other room. Did he go through the door? Yes or no? Was there an intermediate value or position of MLA Shastri at the door? You know, that was the question, right? And that, if you assume that is true, then intermediate value theorem is the axiom. We assume it. Once you assume it, everything else becomes straightforward. You can prove every real number will be part of real number system. No? That is, when you say I got a function f, you got the x-axis here and 2 points over which it is continuous. In fact, all these discussions that we have for these value theorems, all these theorems always assume f is a function which is continuous over a closed interval. See, that assumption has to be made. So I got a interval AB over which f is continuous, right? So I am saying at A, what is the value of this function? There is a value there, right? Whatever value is fa. And at B, I got a value which is fb, right? All it says, intermediate value theorem says, is that any value between fa and fb, if you take, f will always reach some time in between this, in the interval. Any value you take between fa and fb, any value in this. That is, if you draw the y-axis, you will understand what I am saying. fa is the height, right, along the y-axis. fb is this. fa is one point on the y-axis, fb is another point on the y-axis. I am saying as x travels from A to B, f must take every one of the points in between, which is correct because f is continuous, remember. So if you draw a continuous line from here, whichever way you draw it, any value on this, you will always find a point there, correct now? Say, back to our geometry, right? So this is intermediate value theorem, which is very nice. Now we have a couple of others which are, they look unrelated, but then also describe the same completeness. One is called the Cauchy completeness. That means the statement theorem is Cauchy sequences are convergent. As a simple example, I'll give you Cauchy. I think I wrote wrongly. I'll just give an example of this Cauchy sequence. You can read about them in the literature, no problem. Cauchy sequence is an infinite sequence of items or numbers or values. I've got x0, x1, x2, etc. up to infinity. I've got that. Cauchy sequence is, definition of that is not just any set of infinite number of items, but they satisfy one particular property that beyond a certain value of n, call it capital N for example, beyond that, all the rest of the values will be within a small band of epsilon. That means it is all the values have to be within a range, as small a range as you want to specify. That means depending on the epsilon that you specify, the n may be different, but once you specify epsilon saying I want 0.1 or something, I can give you n, 10,000, beyond which 10,000 first element, second element, third, till infinity, their differences will be less than epsilon. So they are in that band, within that band. That's the definition of a Cauchy sequence. All we are saying is that all Cauchy sequences are convergent. If you just make that assumption, and where do they converge? They converge to a real number, obviously. So finally they become a real number. One simple example of a Cauchy sequence, we take pi itself. Yeah? Pi, what is pi? I can't write the value of pi because it has infinite number of digits which don't even repeat. I wrote 1/7 correctly, right? Because it is a repeating block of digits. Pi is not repeating, so nobody can write it. I'll start writing it. So 3.14 like that. So now my x0, x1, Cauchy sequence I'll define. What is x0? Is 3.1. What is x1? 3.14. What is x2? 3.142. What is x3? 3. That means I'll keep adding one digit of pi every time to the x. So I get a sequence. So obviously their difference, remember, successive differences keep getting reduced, no? Because 10 power minus 2, 10 power minus 3 and so on, no? Successive numbers, they become closer and closer. So obviously it satisfies that condition of a Cauchy sequence. I am saying it is convergent. That is the assumption. That means pi is real. So Cauchy sequence has come again. Now you see straight away from our infinite number of decimal digits. It is actually Cauchy, something like, I am saying it is the same, yeah. The son-in-law is same as daughter's husband, no? So they are saying that. Maybe there is I don't know which one is bigger axiom and which assumes more. Whether this assumes less than that or not is a philosophic question I have not been able to answer, right? At least the extreme value, intermediate value theorem was a little more weaker looking axiom, saying that, but then that also is very strong, really speaking, because now you see the image of a function. I got take this intermediate value theorem that we had, I got an interval AB, right? And f takes the value from fA to fB, right? It may actually take a value which is bigger than fB also, possible, right? So, or maybe it doesn't take, doesn't matter. In any case, probably it may take even less than FA also. So let me just write a slightly different graph here. It may look something like this, correct? So which means on the y-axis, if you see, I got two numbers here. One is the minimum here. I'll call it C, and a maximum here. I'll call it D, correct? So as x ranges or changes from A to B, actually f changes from C to D, right? All we are saying is that this itself is a closed interval. That means the image of f, value, all the values of f, if you take them together and put it in one set, that is a closed interval. C comma D is a closed interval. From A to B, f maps to C to D. Every point there will have a corresponding point from in A to B. So it is actually, this intermediate value theorem is quite a strong, that is just a corollary. Now you can prove that by a single, once you have a single point, you can have other points also. No? So it's not a weak axiom as such. It is quite a strong axiom. It doesn't matter. Probably our decimal digits is very strong. That may be slightly weaker than that. I'm not sure which is weaker or stronger. Next, I'll write one more. There are many more. I'll just write one more here, which is the nested intervals theorem. This is again practically same like decimal system. Nested intervals theorem. That means I got an interval between 2 points. I got a closed interval. I want to nest another interval inside this. It may be this half, that half, middle, doesn't matter. We are not specified, right? So I got one more. So I got this interval here. Within that I have another interval. Within that I have got one more interval and so on. We make sure that each successive interval is smaller than the previous one. At least some smaller. How much smaller you decide, right? If we keep doing this infinite number of times, so keep nesting the intervals infinite number of times, all it says is that finally you will have one interval which will contain a real number. That is known as nested intervals theorem. You want to take that as a definition of real numbers, you can take it, no problem. Okay. Now these are the kind of things that people discuss, and now if it is not already been done, as a mathematician you can say, I will assume intermediate value theorem as an axiom and give you proof for least upper bound, extreme value, Cauchy sequence, nested interval, and infinite number of digits. I will prove everything else. Becomes a thesis, you understand. I am telling you how mathematicians keep themselves busy. It's not a big deal. Okay, fine. That's not the point that I am trying to make also. There are a few more there. Doesn't matter. I don't think we are interested in that. My interest in this whole business was only one theorem which I want to take it up, which is this extreme value theorem. Because from this extreme value theorem, we derive one very important theorem called the Rolle's theorem. I'll tell you what is Rolle's theorem. And from this Rolle's theorem, we derive one more value theorem. We already have a extreme value theorem, we have intermediate value theorem. We have one more value theorem, which is called the mean value theorem. And mean value theorem is used for proving the approximation of Taylor series, that is Taylor's theorem. We can assume our earlier axioms and prove Rolle's theorem, or we can prove mean value theorem and so on, so that's okay. But they do it using extreme value theorem. It's not a big deal in that sense, but we have to assume one of these. There are a few more I did not write. You can refer to them if you wish. Then you can prove everything else as proper theorem. Now Rolle's theorem becomes a theorem only now, whereas extreme value theorem is an axiom, or intermediate value theorem is an axiom. But Rolle's theorem is a theorem, mean value theorem is a theorem, Taylor's theorem is a theorem. Everything becomes a theorem, and that brings in that rigor that we want theorems. We don't want implicit assumptions. We don't want axioms, but we have to assume some axioms, so we'll assume some. But once you do that, once you finalize the axioms, I don't want to make any more further assumptions. Correct now? Now, with this, I'd like to get back to the earlier discussion we had about the roots of polynomial equation. I said odd degree polynomial has got at least one real root. But then what happened to the other roots was the question, right? You understand. What happened to the others? Where are they? Where are they gone? No? Even degree polynomial, all the roots are gone somewhere. They are not there. Correct now? That is, they are not in the real number system, really speaking. So that means we need, in spite of this completeness that we have done, all possible reals we have pushed them into one set, still does not satisfy a simple thing like solution of a quadratic polynomial. Roots of a quadratic is even degree. May not have a root at all, no? That is, root in the real number system, it does not have it. So we'll take one simple example and see what people have done to it and what specifically Leonhard Euler has done to it. I think that is the interesting part. You want me to prove Rolle's theorem, mean value theorem? I'm not sure. I don't know if it's part of the syllabus for you. You can refer to them. They're very simple. Rolle's theorem is very simple. I'll state them anyway for you to understand. I'll just state the theorems. Implicitly, you will say it is correct anyway, but you have to prove it using extreme value theorem, right? So what is Rolle's theorem? Very simple. I got a function. This is the x-axis. When I plot the function, which obviously continuous over closed interval a comma b. I mean that, please keep that in your head. Don't change that, okay? So a comma b, it's continuous. That fa is same as fb. Both are equal. Both are equal. They are not different. fa is equal to fb. That means if I were to draw a graph, for example, I can draw a straight line, of course, but I will draw a curve. Supposing I draw a curve, that means I have to go up first and then I have to come back down only, because it has to come back to the same value, no? If I go up, I'll have to come down also, right? Or if I go down, I'll have to go up also. There is no question. Which means there will be some kind of an extremum. Extreme values theorem definitely says there is an extremum, maximum, and at maximum, what is the value of the slope? Direction of the car that we are driving, drive a car from A to B, and the direction of the car is horizontal there. So, what is that? So, there is a point C in the interval where f prime C is equal to 0. Slope of that curve, slope is the derivative, first order derivative is the slope. Slope of the curve is 0 at that maximum or minimum or even inflection point. What we call an inflection. I can have an inflection. It looks like it is going to become a maximum, but then it goes up again. So at that point also slope is 0. Okay, that's known as an inflection point. So in this case it is a maximum only. It will have a maximum. Extreme value theorem says you must have a maximum. At maximum, obviously the slope is 0. Correct? Because it is continuous. We are talking of continuity. Without continuity, if there is a break, of course, it may not happen like this. It will not have a 0 slope. I showed you while driving the car. With a smooth driving of the car face must become horizontal at some point. No? Definitely before it has to come back to the same height. That is Rolle's theorem. F prime C is equal to 0. If you want, I can prove it. No problem there. Because you see, when you have a maximum, actually all you have to do is take the limit of the slope, take the maximum point. If you take the left side limit, you can see it's always less than, no? That means the slope is positive. If you take the same slope as a right side limit from the right side, you will see it's always negative, no? So obviously at that point it becomes 0. This side always positive is always negative. It has to hit 0 there. So simple theorem to prove. Mean value theorem is basically generalization of the same Rolle's theorem. Right? I can write the same diagram here with a slightly different diagram. So I got the x-axis. As usual, I got a point A and a point B, and I got a curve. So FA is one point. FA is not the same as FB. They are two different values. When you got two different values, I can join them, and that line if you recall, if our parikramana of the circle, if this is the circle there, this is actually known as a secant line. This line is called the secant. It's not secant, it is called the secant line. Secant line. Now, mean value theorem, all it says is that there is a point C between A and B where the slope of the curve is parallel to the secant line. Which if you drive the car, you will see. Supposing I am driving the car from FA to FB, right? I am driving the car from this point on a road. Supposing I am able to drive straight, yeah. That means I am facing that B all the way, like this, right? Throughout it is parallel. There is no question of being parallel, it is the same, direction is the same. Whereas, if I have to start somewhere up like this, to come back to that point B, I must go back. At some point, it will become parallel to the secant line, and then it will go beyond that. Whereas, if I go down like this, to reach that point FB, I have to go up like this. And at some intermediate point, you can see it becomes parallel to the secant line, and then it goes up. Correct. In fact, this is the same as Rolle's theorem, except that FB was not same as FA, or keep FB different here. Supposing I take physically, just imagine I am modifying this geometrical diagram that I have, visualization, just a visualization. I take this point and bring it straight down here to make it equal to A, so the whole curve is bent like this. then that secant line becomes horizontal. No? It becomes Rolle's theorem. If you want to do that, that means, how do we do that? At every point here, I want to bring this down so that it becomes equal to Fa. Correct? So how much I have to reduce? At this point, I have to reduce by this much. Here, I have to reduce by less and so on, right? I have to reduce by the height of that the secant line at every point. At every point on this curve, if I reduce by the corresponding height of the secant line, that curve moves down like this, right? And what is that? We can define a new function, call it gx equal to our old function fx only, fx minus, I reduce this now, minus, and what is this height? You got similar triangles here. This difference is fb minus fa. Correct? And this difference is b minus a, correct? This is the slope actually, b minus a divided by b minus a, and I have to multiply by this. Then I get this height, multiplied by x minus a. Supposing I define a new function, which is gx fx minus b minus fa divided by b minus a multiplied by x minus a. What I am doing is actually pulling this down to this, so that the whole curve is bent down. No? So exactly I am doing that. In fact, you can calculate what is the value of ga x equal to a, so it is fa, correct? Minus x is a, x minus a is 0. Fa, Ga is Fa, this is 0, no? So, and what is Gb? Fb minus Fb minus Fa divided by b minus a multiplied by b minus a, because x is b now. Correct? Gb means x is b. So that means minus of Fb minus Fa. This is b minus a divided by b minus a, which is 1. And what is this? B minus Fb F is equal to Fa. So now I have got a new function called gx, whose value at Ga is same as the value at Gb. Both are same, equal. It satisfies the Rolle's theorem requirement, which means there is an intermediate point between the two, call it C, this is a C, where G prime C is equal to 0. This is Rolle's theorem, right? What is G prime C? We can differentiate this. So what is G prime C? Is F prime C minus, I'll substitute it. Actually, I should find F prime, G prime X and substitute X equal to C. Anyway, I'm doing that one shot. Prime C minus, how much is this? Fb minus Fa divided by b minus a. And this is 1, no? Other one is a constant. Is equal to 0, of course. Therefore, what is F prime C? I can transpose that side. Is Fb minus Fa divided by b minus a. What is F prime C? Fb minus Fa divided by b minus a is the slope of the secant line. So, slope of that function f at that point C is the same as slope of the secant line. So, that is mean value theorem. Okay. This is what is used in Taylor's theorem. I would like to stop it there for the moment, and we'll go back to our algebraic problem. I just want to discuss that to introduce a new branch of mathematics I have not done so far, which is complex numbers. We never talked of complex numbers. It's a good time. It just takes 5, 10, 15 minutes to give you the entire summary of complex numbers. We'll do that. Now, our problem, let's start with a clean slate. We had, if you look at a quadratic equation, we had a problem that it has got, probably it's got no real roots at all. Possible. And in fact, we can take the simplest example of the quadratic equation, which has no real roots. Fx x squared plus 1. In fact, what I should really do is, when you say quadratic equation, if you recall, our Al-Khwarizmi is our friend who gave this series of steps, steps to solve quadratic equations using Algebra and Mukabala and so on, right? That's why algebra came into the being. So for quadratic equations, what are the steps he has given? Maybe a simple way of doing that. So instead of taking x squared plus 1, let me just take that now. So what is our quadratic equation? Or quadratic is ax squared plus bx plus c equal to 0 is what we want to solve. In this again, a cannot be 0, definitely, because if a is 0, then it is no more a quadratic equation. Similarly, c cannot be 0, because if it is 0, then again x equal to 0 is one root and other one is not a quadratic equation. So a and c both are not 0. Simple assumption. So what are the steps given by Khwarizmi, right? He says you have to complete it. Completion means what? Basic steps are completion and balancing, right? Completion is completing the square. So I want to complete the square here. That is a monomial square. What is a square? We know one square by heart. What is that? A plus b whole square. We know what is a plus b whole square, or x plus y whole square is a squared plus 2ab plus b squared, right? The problem is, what is this a here? There is one more a here, one more b here. I mean, that's not the ab that we are talking of. Really, we should visualize a plus b whole squared as not a plus b whole squared, but a can be anything, right? So b can be anything. So what we'll do is we'll say something plus something else whole square is equal to, it will be something squared plus 2 something multiplied by something else. It's not something else, it is the same thing else, of course, no? Plus same thing else square. I'll write it as something else square. So we should always visualize a plus b whole square like this. So now, I want something square plus 2 something else square. Now that is the completion of square. Here, do I have something square? X square, unfortunately, if you can treat that. What is the square root of this? Is square root a multiplied by x. Take root a x, I can do that. Square of that will be that. One method. Other method is simpler method. Probably is we just simply multiply by a throughout. So that I get a nice square here. At least something square looks nice, So we'll multiply by a first step. So write it as a squared x squared plus abx plus c equal to 0. Simple. AC. Now a squared x squared. So it is something squared. So we'll write it like that. So something is ax squared plus I must get that. 2 multiplied by something which is ax multiplied by, I can only write something else now. What I should write? Actually, I want to get abx. But I got 2ax here. A is there, x is there. So I got a 2 instead of a b. That means I have to multiply by b by 2 then I'll get ABX. Correct? No? No problem there. Plus B. I have written the first two terms now. Now we'll write the third term. Third time, I want something else square, of course. What is the something else now? B by 2, because now you written 2 something else. So I write something else square is B by 2 whole square. I have to write it. But unfortunately, I don't have it here. I have AC here, but now I am forced to write B by 2 whole square. Therefore, I have to say plus AC minus B by 2 whole square. Correct, no? Equal to 0. Now, A plus B whole square contains only this much. So, we keep only this much. Now, we do the mukabala, balancing. So, we transfer everything else to the other side. So what is this? This is AX plus B by 2 whole squared. This much. We keep it this side. Equal to, take the other side, is B squared by 4 minus AC. I can do some division here, common factor by 4, B squared minus 4AC by 4, right? Correct? So now we take a square root. So AX plus B by 2 equal to square root of B squared minus 4AC divided by 2. But then we know that x squared is same as minus x squared. No? So both are same, minus into minus is plus. So I should really write plus or minus. So what is x now? X is what we want. I'll write AX first. AX is equal to minus B by 2. So I write minus B plus or minus square root of B squared minus 4AC by 2. Correct? That's right. And I want x. So take the balancing. Take the x to the other side. So x will be minus B plus or minus square root of B squared minus 4AC by 2A as we by hearted, which is correct. Everything is fine. Everybody is happy provided I can take the square root. Now the problem is, can I take the square root? Yes or no becomes the question. No? So that is the basic question of quadratic equation, which is even degree. No? So there are three possibilities here. I got a B squared minus 4AC. What are the three possibilities? One is it can be 0, happiness. If B squared minus 4AC is 0, what happens? I get x is equal to minus B by 2A, a single root. Right? There is no plus or minus there. No? You understand? So it is known as a multiplicity of root. Same root twice, that's what we have to say, really speaking. Minus B by 2A is the root. Again, minus B by 2A itself is the root, twice. Same root twice. Copy of the same root. Or this can be greater than 0. Happiness, I get two distinct roots. Both are real, no problem. And less than 0, I can't take square root at all. So there is no root. It's a real line. So in fact, you got the three cases here. When it is 0, I got the x-axis, right? If you plot the different binomials, 0 case will be something like this. It touches x-axis only once. Greater than 0 case will be, it intersects x-axis twice. There will be two real roots. Less than 0 case will be totally above x-axis. Doesn't touch at all. So this is the case now. So now the thing is, if we can somehow take the roots of this quadratic as part of our system, no? So that is the question. How do we do that? Because once we do that, remember, we are doing only plain algebra here. We are following those axioms of field, like I discussed, commutativity, associative, blah, 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 correct now, everything. What the real numbers followed. And if we somehow visualize, we have to imagine. We imagine some intersection of this curve with the x-axis saying that is a value, right? They will definitely follow the same rules because we are using only algebra, right? That is, so we have to imagine that, the imaginary numbers. So I will take the simplest example of that imaginary number, simplest quadratic, which gives you imaginary numbers. x squared plus 1 equal to 0. Here, square root of minus 1, it doesn't exist. Plus or minus. So there is a minus square root of minus 1 also. These are the two roots of this x squared plus 1, because when you square root of minus 1, I get a minus 1. When you square minus square root of minus 1, you get a minus 1 only. Minus minus becomes plus. But the square root minus 1 is minus 1. Both are minus 1 only. So x squared plus 1 becomes 0. So if you can just imagine square root minus 1 as is like a virus. Yeah, some virus. You can just imagine some kind of a virus which is there, right? It doesn't mix with real numbers. It is separate. It is always separate. You can always separate it out. No? When you multiply with a number like 4, it will become 4 times that virus. It is there, right? I can divide that also. By 2, it becomes 2 times a virus and so on. So, but virus is there. No? So we keep that separate. But one thing about this particular virus is that these are actually what are called complex numbers. General complex number is a plus. Normally we write square root minus 1 as I, this representation Euler use, I will use that. A plus IB is a complex number. Every complex number has got 2 parts, you can see. The real part is there, imaginary part, they don't mix. You have to write that as plus only. You can't add, there is no addition here. We can't add a real to a complex. No way you can do that, right? I can add a real to a real, a complex to a complex, imaginary to imaginary, but not real to imaginary. But then, when you multiply or when you add, something peculiar happens. We have what are called complex conjugates. Supposing I have one more complex number which is a minus IB. I got 2 fellows here. I got 2 complex numbers. One is a plus IB, other one is a minus IB. In fact, this earlier fellow itself is an example. Square root minus 1 minus square root minus 1, negative part. So imaginary part, one has got positive, other one has got negative real value. If I have this, these are actually known as complex conjugates. They annihilate the imaginary part, whether you add them or multiply them. In both cases, supposing you do an add the 2 complex conjugates, a plus IB plus a minus IB, I get 2a, which is totally real. Virus has disappeared. Right? Similarly, I do a multiply. A plus IB multiplied by a minus IB. Our former famous by-hearted theorem was a plus IB multiplied by a minus IB, a square minus b square, you know that. So it will be a square minus IB whole square, of course, not b square, it is IB whole square, it is I squared b square, I squared being minus 1. So actually I get a squared plus b squared. Real again, both are real. So when you add two complex conjugates, you get real. When you multiply the pair of complex conjugates, you get real only. So that means now you can see complex is like, I got a real line here, real numbers. Complex means we go slightly away, but then we know we keep that part always separate in our calculations. But then when we want, or when it wants, it is going to come back to the real axis again. Understand? It's possible. Now how do we check that out? Or there is another way of representing this polynomial. I will write that and show you also about that multiplicity of roots also. That also I wanted to show you exact algebra of it. Some amount of rigor if you wanted. No? For example, I have found 2 roots for this here. Ax square plus bx plus c equals 0 has got 2 roots. Whether real or complex, whatever, doesn't matter. So let us say I've got the roots as R1 and R2. Now I can have a different quadratic function, something like this. I will take x minus R1 multiplied by x minus R2 equal to 0. And what are the roots of this? When x equal to R1, this is 0. When x equal to R2, this is same. Actually, it's got the same roots. So therefore, this must be equivalent to this, except that the power x squared has got a coefficient of 1 here, but I have got a coefficient of a here. I can do a bit of cheating. I'll add a here, multiply a. So a multiplied by x minus r1 multiplied by x minus r2. I can expand this. No. I got 2. We know how to find a plus b to the power of n. Forget about multiplying two monomials. No, I can multiply these two now. Correct? We can do that. I'll do it. Let's do that. So what is this? The same as ax squared minus a into r1 plus r2 of x plus a r1 r2, correct, equal to 0. Now, if these two, they have the same roots. If these two have the same roots, that means the coefficients are same. So, now I can match the individual coefficients. Coefficient of x is b here equal to minus a of r1 plus r2. Similarly, coefficient of x power 0 is c here. I can match it to a r1 r2. So, I get two equations and two variables r1 r2. If I solve them, I got the roots anyway. So, it's the same. So, I can always write a polynomial of n roots as a multiplication of this x minus root 1, x minus root 2, etc. And if r1 and r2 happens to be the same, that's the multiplicity of roots. I got two roots, both are r. No? So, that is also, that also gets taken care of. And this is the advantage of visualizing something called a complex number, which we never do intermingling operation with real, but then we always keep it separate. Finally, we can always do that. And it always follows the algebra. Remember, we got this by doing algebra of a quadratic equation. So, it follows complex numbers, follow all our algebraic field. They have, except ordering, they don't have ordering. There is nothing less than or greater than you can't apply because they are not on the same axis, right? Other than ordering, it satisfies all other rules. Axiom A is 100% followed. So, we can make it a part of our number system, which means I can have an infinite series where it can be a complex number also. Variable can be complex. So, we take one simple example just as a interest. Supposing we had one, remember we have an e power x, it's a popular infinite series. E power x is 1 plus x squared by 2 factorial plus x cubed by 3 factorial plus etc. till infinity, correct? Is an absolutely convergent series. Any value of x, you get a value, proper value, which is e power x, right? Now we are saying, after all, this is also a polynomial, infinite degree polynomial, and I can have x not necessarily real alone. I can use complex x also, imaginary values also for x, but then I always keep in mind, I keep them separate, but finally I can always match the real and imaginary parts and get some nice results, right? That is the objective. So, as a simple example, we will take e power xi equal to, I want to raise e to the power of x square root minus 1. Actually, is no meaning. What is the meaning of this? It is actually no meaning. I can't raise the power of an imaginary number itself is imaginary, somewhere up there. I don't know what it is. I don't know what is minus 1, root minus 1. Now, I am saying you want me to raise e to the power of that imaginary number. How many times I have to multiply e by, what is e power x is multiply e by itself x number of times, no? That's the meaning of e power x. Now, at least e power half I could understand. Half number of times is square root or whatever. Right? Why is that? Also, see, e power half, multiply e by itself half number of, not 2 number of times or 3 number of times, half number of times. Has no meaning, actually has no meaning. What we do is something very simple. We multiply this by another e power half, correct? I get two numbers which are same. I don't know what it is, but they are same, right? And what will you get? Remember, when you multiplied e power x and e power y, we got the answer e power x plus y now. So, I can do that. Will be equal to e power 1, which is e. Therefore, e power half must be square root of e. So, I can visualize that at least. In this case, there is no way I can visualize e power xi. I don't know, but then we'll expand, we'll do the algebra for it anyway and try to understand is 1 plus xi now, right? Plus xi plus x squared I squared by 2 factorial plus x cubed I cubed by 3 factorial plus x power 4 I power 4 by 4 factorial plus etc. Yeah, but now I know I is square root minus 1 known. What is I squared? Minus 1. No problem. What is I cubed? Minus I. Multiply I squared by I get minus I. And what is I power 4? This multiplied by another I, which is minus I squared, which is 1 again. And multiply, what is I power 5? Back to I. So this is like our derivation of sine. This is like when we derived sin x, saying sin x becomes cos x minus sin x again, minus cos x, back to sin x again, repeat. No, same way here. Square root minus 1 minus I, 1 again square root minus. Keeps repeating. So we just have to substitute those values here, equal to 1 plus xi, I is I only, I can't change anything. 1 plus xi, I squared is minus 1, therefore will become minus x squared by 2 factorial, then minus I cubed is 1 I will come there. So x cubed I by 3 factorial plus I power 4 is 1, x power 4 by 4 factorial plus x power 5 I by 5 factorial minus x power 6 by 6 factorial and so on. Understand? So I get 1 I minus 1 minus I, 1 I minus 1 minus I. So that repeats. So equal to. Now as usual, I got virus in so many places. I got non-virus. We'll collect all the real into one group, all the virus into other group, so that we can use them later. It will be 1 minus x square by 2 factorial plus x power 4 by 4 factorial minus x power 6 by 6 factorial plus etc. Infinite series plus I. Now all the rest have I as one common factor. I take I as a common factor. X minus x cube by 3 factorial plus x power 5 by 5 factorial infinite. Now these two infinite series have we seen before? The Madhava series, yeah. I got a cosine series and a sine series. I got both. I got both in the same. So we'll write that. Equal to, so what is e power xi cos x plus I sin x. Fantastic. This is one of the Euler's equation. Correct? Now one special value. What is e power pi I? That is x is pi. What is cos pi? Cos 180 degrees is minus 1. Sin pi is 0, so that is 0, right, minus 1, or e power pi I plus 1 equal to 0. Whatever that means, actually there are e power pi I don't know what it means, but plus 1 is 0, as per our algebra. Now cos x plus I sin x, this is called Euler's equation. Now this, in exponents, when we multiply, we get addition, no? So we can do some small set of tricks there. I'll just show you one trick in that. Simple trick. And we get a theorem, old theorem, and a one-line proof for an old theorem. There was a theorem called de Moivre's theorem, who said with great difficulty he proved it, saying cos x plus I sin x to the power of n, where n is an integer. I can raise it to any power. No? So I got a complex number, cos x plus I sin x, to the power of 10, 12, whatever. No? So he said de Moivre's theorem says this is same as cos nx plus I sin nx. So this is de Moivre's theorem. Actually, de Moivre's theorem. Now you want to prove it here. What is I got cos x plus I sin x is e power xi. We got that here. So this is equal to e power xi to the power of n, right? Is e power nxi, which is equal to cos x plus. That's it. Half-line proof of de Moivre's theorem with this simple trick there. Now we'll take two examples. Now this has no meaning actually. If you want to use this that I has got to be removed by some complex conjugate business, right? How do we use that? We'll take a simple example. Cos x plus I sin x whole square. Just square it. Will be same as cos 2x plus I sin 2x. Correct, no? De Moivre's theorem. So this side we leave it as it is. So what is the left side? Cos squared x plus 2i sin x cos x minus sin squared x. This is minus sin squared x because I squared is minus 1 equal to cos 2x plus I sin 2x. So now I got a nice equation. Both have got real parts and imaginary parts. I can always match the real part and imaginary part. They have to match because they don't combine. No? So therefore, what is cos 2x? Cos squared x minus sin squared x. In fact, if you recall, cos a plus b was cos a cos b minus sin a sin b. A and b both are x. Cos a plus b will be cos 2x. Cos a cos b is cos squared x. Sin a sin b will be sin squared x. It's correct. No problem. Then sin 2x will be 2 sin x cos x. Sin a plus b, sin a cos b plus cos a sin b. And a and b both are x. Then it becomes 2 sin a, 2 sin x cos x. So this equation. So using this De Moivre's rule or theorem, cos any cos 3x, cos 4x, cos 5x, you can find all of them as functions of cos x and sin x. So that's a beautiful theorem. But then the theorem itself is half-line proof using this exponential power, using the Euler's formula or theorem, what you call it. So that means this brings, because this complex also follows all the rules of algebra, we can do complex arithmetic as part of it. Now, finally, I will state the correct first theorem of algebra. Now, we require this much background. So, what is the first theorem of algebra? Is for an n degree polynomial, whether odd, even, doesn't matter. Nth degree polynomial. Now we have the some confidence to deal with complex numbers also. So with complex coefficients. Has at least one complex root. Of course, once you have one complex root, the other n minus 1 roots can be found. That's a different issue, but the theorem stated is nth degree any polynomial, any non-trivial polynomial with complex coefficients has at least one complex root. That is the definition. But then if you have real coefficients, remember we expressed a real polynomial, one last explanation to make your ingestion, not injection, ingestion of complex numbers a little more stable. No? See, ingest any knowledge, you have to ingest it. You have to eat it first, of course. Eating is looking at it or looking at a video or listening to somebody lecture. Eating. But then just eating is not enough, no? Unless whatever food you eat, you have to digest it properly. You have to ingest it and digest it properly. Otherwise, it simply goes away, right? Without giving you any help. So we have to ingest the knowledge properly. Just for that ingestion, let me just write one last statement. Supposing I have a polynomial which is an x power n plus an minus 1, n minus 1 plus etc. a1x plus a0. Now, these are real coefficients, not complex. and I get n roots obviously, correct, which may be complex also. So I get n roots which may be multiple also, that is same root multiple times also is possible. N roots, we'll call them R1, R2, etc. up to Rn. So I can rewrite this polynomial by a new way of writing it is an we multiply so that x power n will get the same coefficient, x minus R1 multiplied by x minus R2, etc. up to x minus Rn. This will be equivalent. Now both will have matching coefficients. That means whether these R1, R2 or complex or real doesn't matter. When you multiply and add those quantities, they will somehow adjust and get back to you only real coefficients. 100% guaranteed. That will always become real. That means if you have a root, let us say Rk root, which is some C plus Id is the root. One of these roots. Its complex conjugate also must be a root because this has to be cancelled. This imaginary part has to be removed. Yeah? When you multiply, this imaginary part has to vanish. No, it has, because it has to become real coefficients. Therefore, then C minus Id will definitely be also a root. No questions on it. So complex roots of a real polynomial will always appear in as pairs only. It cannot be separate. I'm not talking of polynomial with complex coefficient. That can have complex root, single root. Whereas a polynomial with real coefficients can only have complex roots as conjugate pairs. There is no question. That is why when n, whatever value of n is there, if it has got complex roots, it will be always in pairs. And if n is odd, there will be one left other than n number of pairs. No, that will be the real root, which we discovered as the old version of theorem saying odd degree polynomial must have one real root, whereas even degree all the roots can be paired up as pairs of complex, which means there may not be any real root at all. Correct? Just to some understanding of this whole business. There are many more very interesting things which Euler has done beyond this point. Euler has worked on number system also, number theory also, worked. Brilliant mathematician. Of course, we have our brilliance here. Like I said, Indians also have, Madhava was one super brilliant astronomer and mathematician, Parameshwara, all those people there, Kerala School of Mathematics. And we say Kerala School, but that Kerala part, remember this Kerala School in Sangamagrama, that Kerala was actually part of our Vijayanagara Empire. So Madhava's king was Devaraya or Krishna Devaraya, no? Our king only, our man only. He used to speak, I think, Malayalam, but he's actually a Kannada fellow. No? So, I'm saying the Karnataka Empire. Vijayanagara Empire used to be called Karnataka Empire. So actually, Kerala School was part of Karnataka Empire. And Karnataka Empire, as you know, if you see history, especially Sri Krishna Devaraya, he promoted music, dance, Shilpa, that is sculpture, mathematics. Also. Mathematics is another example. They don't mention it, mathematics. Music, for example, the greatest of greats musician, who is the grandfather of classical music, Indian classical music, Purandaradasa. And Purandaradasa was in Sri Krishna Devaraya's court only. He was there. He was encouraged by Krishna Devaraya. So he gave that much of support to these arts and maths and astronomy and astrology and so on. So our people, all I am saying is that all you need is a bit of encouragement from somebody else. No? So I mentioned in some of my earlier talks long back that I got a very great encouragement from my family. My brothers, I have lots of brothers and parents and uncles and so on. No? That's why I could learn very fast. And what was the encouragement? Not a piece of chocolate or something, no. After finishing the exam, he'll come, have you done well? Very good. Then he'll pat me on the back. That is the encouragement. I'm saying even that much is enough for people to get interested in a subject and do well. So, I'm hoping that all of you will think in that direction. No? I mean, think that whatever you have done so far, all these days, doesn't matter. Whatever you have scored, in fact, marks also many times doesn't matter, really speaking, whether 70%, 60%, 50%, 90% may not even make a difference. Like I said, Srinivasan, Ramanujan was a 10% student throughout his schooling. Right? May not, but in this modern times, percentage also has a meaning, doesn't matter, right? But if you want to improve that, your knowledge has to improve. Basically, it's not by hearting. By hearting is a must of multiplication table and algebraic formulae like a plus b whole square and trigonometric function like a by sin a equal to b by sin, that one. And then differentiation of trigonometric function like sin x, cos x minus. A few things you have to by heart. I mean, there is no choice, but you should know actually how they work also before you actually by heart. Once you understand it, then you by heart. Understand and by heart. Digest and then appreciate what is the good food that you ate. So that is there, right? So you do that and you will see a dramatic improvement over a period of time. At least a satisfaction. If not marks, you will get satisfied saying, yes, now I know what is this. I understand what is a quadratic equation. Why what Al-Khwarizmi did was so important in Europe. Because nobody did that. No, algebra was not there. No, systematic way of, I showed you exactly how he would have solved that quadratic equation. And that is how it should be done. And he showed it first time in the world. So you must pay a huge tribute to Al-Khwarizmi. And we should, of course, equally pay tribute to Brahmagupta and Aryabhatta and Bhaskaracharya, who actually designed those algorithms of quadratic equations, right? But they gave it in terms of some Sanskrit poems. They are not interested in distributing the knowledge to public, I think. So that is a different issue. I mean, that's a different question. But then we have to pay tribute to all of them, right? And by doing that, I think we get part of their knowledge. No? That is the idea. The general idea is, I always pay tribute to HRS because I wanted a part of his knowledge. That's a trick, no, that you have to employ. So I hope all of you will be able to do a little better than what you did till yesterday. That is all I expect. I am not expecting some great stuff from all the people. But I am expecting that you people do a little bit, a little 1.1% better than what you did yesterday. If you can achieve that, I think what I have done so far, I am happy with that. I am happy with that exercise that I am doing. I have sweated out, you can see. Great sweat, right? But then I will assume that what I have done, I am happy with what I have done. If it helps even one of you, some of you, to improve your understanding, not just mathematics, any subject you have to analyze in a style. I have tried to indicate some styles of thinking, and you follow those styles of thinking, I am sure you will be able to do better. Okay? Thank you very much for the patience that you have shown in watching this video for so many hours, but 19 hours or something. You have done that. It's great. And for that at least, because you watched for so many hours, your knowledge must be better. Let us hope it does that. Okay? Thank you all.